As we know, proteins are one of the classes of biomolecules that we'll be talking about in this class. Proteins are polymers. That means they're made up of chains of repeating units. Now, proteins are an example of heteropolymers. That means the units that are repeating are not all the same, but they have slight differences. And as you probably know from your earlier classes, these units, the building blocks of proteins, are amino acids. So there are 20 different amino acids that are used in different combinations to make up different proteins. So in this video, we'll first go through the common features that all amino acids share, and then we'll go through the differences that make the 20 amino acids unique. So let's start by drawing the basic structure of an amino acid. Here's what the basic structure looks like. And now let's identify the different parts that we have here in our structure. So this central carbon is called the alpha carbon. Attached to this carbon, we have a hydrogen, and we also have this R group, or side chain. The side chain is the thing that distinguishes the 20 amino acids from each other. So this group is different for each amino acid. Then on either side of our alpha carbon, on the right, we have a carboxylic acid group, and in an amino acid, the pKa of this functional group is around 2. Then on the left, we have an amine group, or NH2, and the pKa of the conjugate acid of that amine group is 9 to 10. The amine group and the carboxylic acid group together give us the name amino acid. So now let's think about if we have our amino acid under physiological conditions, so pH 7.2 approximately, what will be the charge state of this amino acid? So take a moment, think about these pKa's, and see if you can figure out what the charges on these groups will look like, if there are any, under biological conditions at pH 7 or 7.2. So for our amine group, the conjugate acid there has a pKa of 9 to 10. That's greater than our pH, so that means that this group will be protonated. Conversely, our carboxylic acid group has a pKa lower than our pH. That means it will be primarily in the dissociated form. So in the end, we have at physiological pH at around pH 7, a species that has both a positive and negative charge. This is called a zwitterion. That's when you have a full positive and full negative charge, and overall no net charge, because those two cancel each other out. So if we look at our alpha carbon, again, our central carbon, we can see that we have 4 different groups attached to it. And that's the case for all except one of our amino acids. So you might remember from organic chemistry that this means that this is a chiral center. So there are 2 different ways that we can arrange these 4 different groups around the central carbon. And those 2 compounds with the different arrangements are enantiomers of each other. It turns out in biochemistry, when we have amino acids that are in proteins, they all are the same enantiomer. They're all the L enantiomer. So you may remember using R and S designations in organic chemistry. In biochemistry, we use L and D, which have to do with how the compounds rotate plane polarized light. But we won't go into the details of that. What's important to know is that we just have a single enantiomer. Interestingly, that's one of the biggest things that confound people who study the origins of life, is how, as you might remember, enantiomers have very, very similar properties. So how do biological systems end up with one single stereoisomer in almost all cases, when it seems like the two should have been equally accessible? So those are the commonalities between amino acids. Now what we want to do is go through the different side chains to see what they look like and what different properties we might be able to expect among different amino acids. So first we'll talk about the hydrophobic side chains, or nonpolar side chains. And we'll go through the name, the abbreviation. So you're expected to know the 3-letter abbreviation, but not the 1-letter abbreviation, and the side chain structure, which you'll also need to know. So our first amino acid is glycine. And it has the side chain of just an H. So this is the one amino acid that is not chiral because the central carbon has 2 hydrogens attached to it. And we'll see it has unique properties in terms of flexibility. One other thing to note is that glycine is not particularly hydrophobic, so you'll need to look out for the sequence context to figure out whether glycine is acting as a hydrophobic or hydrophilic amino acid. Our next one is alanine, with the abbreviation ALA, and that has a CH3 as a side chain, so it's another relatively small hydrophobic side chain. Next we have proline, or PRO, and this amino acid is very unique in that it has a cyclic side chain. So the first carbon branches off of the alpha carbon as normal, and then this third carbon connects back to the amine group. Next we have valine, or VAL, so we get to a little bit more of the bulky hydrophobic amino acid side chain groups with this one. Continuing in that vein, we have leucine, which is another bulky one. And like valine, branched. And isoleucine is an isomer of leucine. It has the CH3 group coming off of the first carbon in the chain. Continuing our hydrophobic amino acids, next we have methionine, which has a straight chain with a sulfur in the middle. But sulfur isn't very electronegative, and it doesn't have a hydrogen attached to it, so this is still nonpolar. Next we have phenylalanine, which is the first of our aromatic side chains. So it has a CH2 and then a benzene attached to it. Next you have tryptophan. So tryptophan is also aromatic. This one's a bit tricky to draw. So attached to our CH2 group, we have a 5-membered ring, which contains a nitrogen. And then attached to that, we have a 6-membered ring. See, mine turned out really lopsided. That's not very beautiful. And the nitrogen has a hydrogen attached to it. So these two are our first two aromatic amino acids. And another thing to know, which arises from their aromaticity, is that they absorb light at 280 nanometers, which is helpful when we want to quantify proteins. So those are all our hydrophobic amino acids. Next we get to the polar uncharged amino acids. And our first one of those will be serine. So serine has a hydroxyl group. So it's CH2OH. Next we have threonine. So this one has an additional methyl group compared to serine. So threonine can actually be relatively hydrophobic, and it's not surprising to find that one in the interior of a protein. Tyrosine is another aromatic amino acid. So this one is like alanine, except that our benzene ring has an OH group on it. So this is another amino acid that absorbs UV light. And this is the first one that we have a pKa value that you'll want to know. So the pKa for this hydrogen attached to the oxygen is 10.9. So most of the time, this will be uncharged. Asparagine is one of two amino acids that has an amide group in the side chain. So we have a C double bond O, NH2. Glutamine is the other one. So it's like asparagine, except that it has an additional CH2. We have CH2, CH2, then carbonyl, NH2. So this is an amide group, different than an amine. Cysteine is a thiol, so it's CH2SH, and the pKa for this group is 8.1. So that's relatively close, or 8.2, sorry. That's relatively close to our physiological pH. All right, so next we have amino acids that are typically charged under physiological conditions. First, we have the positively charged group, and we'll add here for all of these, you'll want to know the pKa values for the side chain. So our first one is lysine, and lysine has a chain of 4 4 carbons and ends in an amine. So the pKa for this charged version of the amine, that's the acidic form, is 10.8. Next we have arginine, which has a chain of 3 CH2 groups, and then a functional group that you may not have seen before, a guanidinium group. That looks like this. And that has a pKa of 12.5 in the acidic form. And then our last positively charged amino acid is histidine. So this one has an imidazole ring in its side chain, which we saw in one of our examples in class previously. So this structure is aromatic, but generally the positively charged aspect is more important, and it doesn't absorb UV light the same way that others do. And the pKa for this one is 6. And last we have our negatively charged amino acids. So these are generally found with a negative charge at pH 7. And so for the pKa, I'll give you the pKa for the conjugate acid, but the structure I'll draw is the conjugate base. The first one is aspartate. So that's the name of the conjugate base. Aspartic acid is how we refer to the acidic form. And aspartate has a carboxylate side chain, so that's a deprotonated carboxylic acid. And the pKa for that carboxylic acid is 4.1. And then we have glutamate, or glutamic acid. That's the acidic form. And that one just has one additional CH2 group compared to aspartate. And the acid has the same pKa value as aspartate, 4.1. Okay, so those are all 20 amino acids that you need to know with their pKa's and some additional facts about them. So we'll be talking more about amino acids and protein structure in our upcoming classes.